So good morning and welcome to this fourth workshop that we're having on MicroSim. And it's a pleasure to see several departments apart from materials that are getting involved, both offline and online. And so we as developers are very happy to see this. So what the morning session is going to be is going to give you an overview of what MicroSim offers. All right, and I'll briefly touch upon what the particular solver that you are going to be using in the afternoon session. Okay, so in the morning, first half of the morning, I'll give you the overview, and then a little bit 15-20 minutes later on, I'll give you an overview of the GPU solvers. So this MicroSim as an initiative was made possible by a National Supercomputing Mission project, which got us developers together who are put here, and also and as you will see later that they are from different universities, but we have gotten together as a common initiative to get this particular software together because we thought that this is a important activity required for any progress that is utilizing phase field type of models. Okay. So these are the list of developers and contributors to MicroSim. They are distributed all over IISc, IIT, and CDAC Pune, and Savitribai Phule Pune University, and they involve PhD students, master students, bachelor students, internship students who have contributed to different parts of the software at different points of time. This is in a nutshell from what the consortium is. As you see, all the partners are listed over here. So now briefly to go into what is why we are wanting to build this software together. And anybody coming from materials, I know you come from math, but there are several people who come from materials. And if you were to write materials models typically, and if you were to study materials phenomena, anybody will know that they span decades of length and time scales, and it is not possible essentially to write down a single model which covers all the aspects or all the phenomena that occurs at the different scales. So it becomes necessary therefore to essentially do write down models specific to a particular scale and then do what is known as scale bridging operations to take information from scales lower down to upstairs, or you take boundary conditions from higher length scale simulations to the respective scale that you are doing. So this is typically what is done to get something done for most modeling exercises. And in a nutshell, this is what is known as integrated computational materials engineering. So some of you might be aware of this activity. So as you see over here, there is a host of models that are relevant at each different scale, and they are mentioned over here. And this will be also in a better depicted pictorially better here, where you go all the way from electronic structure, where you do DFT calculations, molecular dynamics at the atomic scale, accelerated molecular dynamics at slightly higher scales, finite element calculations at the continuum scale. But what is relevant or what is important for the materials and what is a connect between the continuum and the electronic scale calculations is this mesoscopic scale calculations, which essentially is related to the microstructure of the material. And as you will look in most materials problem, this seems to be the most the particular scale that influences the properties of a material that would come out of a processing condition. So this is therefore something that one needs to keep in mind, and therefore the importance of phase field, which is one of the most important ways to thermodynamically consistently model material phenomena at that scale. The reason it is so powerful is because of the range of problems it can treat and the predictive capability it offers. So, for example, I will just play these movies for you. This is, for example, a solidification problem which involves directional solidification. So you are essentially solidifying in one direction, and the direction is towards you. It's coming out of the plane of the board, and the question you're asking the model is, how do the phases organize as the solidification happens? Okay. Now this is a predictive question. Why is it important? Because you want to know what microstructure emerges given a particular processing condition, and in this case, the processing condition is precisely of solidification. Okay. Now you see, as the solidification is happening, I am just inputting what I've given as an input to this model is just the thermodynamics and the kinetic properties. And what I'm asking the model is to predict me the microstructure which emerges from the certificate, from the simulation. And because it is able to give this predictive prediction, it becomes a powerful model for this particular mesoscopic scale. So this is, for example, a three-phase eutectic solidification thing. But you can also have simpler cases, but computationally intensive cases. So, for example, this particular simulation is of precipitation in a nickel-based superalloy, where you are essentially asking the question: if you were to heat treat a material at a given temperature, what is the distribution of the precipitates that emerges, and what would be their size distribution, volume fractions, and all of that, which would eventually determine the properties of the material. Further, you can also ask questions all related to microstructure formation, where you're asking questions like failure of materials. For example, here you're asking the question: how would void migration happen in when you are having in your electronic circuits, when you're having high electronic density of current flowing, and when you have these high electronic densities, you typically have migration of the material because of this electronic flux. So this is essentially where material is essentially translating from one end to the other just because of the electronic current that we impose on the material. So this is a failure mechanism. You have essentially void formation, and that is something. So you can not only model microstructure evolution, you can also do failure mechanisms, because failure mechanisms are again in the broad class of category of free boundary problems, where the interface is moving due to a stimuli that you give to it. Okay. Similarly, you can do classical multiphysics problems. So, for example, here it's a domain wall formation in ferromagnetic materials or ferroelectric ferromagnetic materials, which can also be solved using the classical Ginzburg-Landau formulation, which also gives you these structures are important for magnetic properties and electrical properties, which you can derive from these groups. And this is a classical dendritic solidification that of a typical mass. Now, as I said, so this space field therefore becomes a very, very important and powerful tool precisely for this particular aspect, and therefore you need software which can readily do them if you are looking for application questions. Okay, and what we found, if you look at the community of developers, if you look at the open source solutions in the other scales, you have for the macroscopic simulations, several possibilities existing. Electronic calculations still existing fairly mature solvers. For molecular dynamics also there exist fairly mature solvers. But if you look at the mesoscopic simulations, particularly for phase field, the solvers are not as very right as what the other categories of solvers exist, and there is a void, particularly in the category of open source capable solvers, which can utilize high performance computing machines as well as be able to treat a wide variety of problems. So this was our motivation to address this gap, and MicroSim is a development towards filling this particular void. Okay, so essentially this is what we have tried to attain through the construction of MicroSim. So if you look at it, the first aim was to essentially solve the classical phase field problem using different discretization techniques. Okay, if you look in the literature, most PDE solvers are based on finite element based. Okay, and if you look at the phase field solvers in literature, also we have prisms, moves. All of these are finite element based solvers, whereas there are there are solvers based on finite difference methods, but they are commercial. So we thought of addressing this void of discretization possibilities by having solvers in our repository which have all these discretizations possible. Okay, so this was the first thing that we did. We have finite difference, fast Fourier transform, and the finite volume based methods that can be that are possible to have in our model. Second is, if you were to look at it, the possibility of having different hardware. So typically in most National Supercomputing Missions,
You are able to use it because it's not fully clear.
Not clear. Okay, so is it clear now? Hello. Okay. So if you look at the hardware that is the phase field models can use, typically there will be either CPU based, GPU based, or so either one of them. And if you look at from an NSM NSM user, you have essentially a big machine allocated to you, but you also land up into bigger queues. So you typically would like to have a software which can use whatever is available at a particular time in a particular machine. So you would like to solve the same problem, but the hardware is a limitation because of the availability, and you would typically want to deploy whatever is available to you at that particular time. So this becomes a problem to tackle, and that's what we have tried to address, to have the same problem that can be solved either by the CPU or the GPU or a combination of the both. Okay, so this is something that we have tackled in our repository. Third, and very critical, if you really want to have phase field impacting the metallurgical or any materials community, you would need to talk to thermodynamic databases, because that's your connect to the real world in terms of the thermodynamics that you write down. So we have developed a strategy where we can essentially interact with both commercial TDBs and open source TDBs. TDB stands for thermodynamic databases, and thereby you are able to model real alloys for realistic conditions, thereby giving you realistic predictions for metallurgical process conditions. Okay, so this becomes quite useful. And fourth, as you will go through, you will find that interacting with phase field, there is already a lot of literature that you need to cover to understand what is the state of the art in the phase field literature is. So to basically get you started, it's this, we have developed a graphics user interface which allows you to get initiated to what phase field offers. Thereby, once you get that visualization of what phase field offers, you then are in a better position to actually read the literature and get yourself acquainted with what the details are. Okay, so it essentially is a interface that allows you to, jumpstart your understanding of phase field, and this is therefore a very nice framework which allows you to take input files, visualize the output, and also do post-processing of the solvers. Okay. So these are coupled together in a singular interface. And finally, this is not particularly that relevant, but still it's something that of interest. If you look at most commercial phase field solvers or open source phase field solvers, they will mostly be connected to one particular model. If you look at phase field literature, you have different modeling models that you can write down, because the formulations are still evolving. Okay, but if you essentially each of them is for a particular class of material problems that you can solve, and what we thought was would be nice was to integrate all of them and have solvers available for all of these strategies that are there as a state of the art in literature, thereby giving you a wide range of things to play around with. Okay, so this is something that is present in very few solvers around the world, and this composite flexibility that you have in this graphs sitting over here is not there in any solver that is present in the world today. So in that sense, this effort is unique and stands out in the community. So this is a snapshot of what MicroSim offers in terms of its capabilities, what I just put out in the other slide, and also the visualization of what the graphic user interface is, as well as the post-processing toolbox offers. Okay. Okay, so a brief, this I will cover when I'm doing the GPU solvers in the later afternoon. I'll give you also a demonstration of how to set up the simulation later. But just for people who might not be knowing, this is where our repository sits in the IISc India GitHub account, where MicroSim is one of the repositories. You can also access our website. This is slightly updated. You can either access this or this, one of them. microsim.co.in is, we own this, so this is our web page. And you also can view our YouTube channels where we have all our videos recorded and uploaded. Okay, so all the sessions we have done until now, workshops, you can essentially go through them in a very at your own pace and get yourself acquainted what this solver offers. Okay, so just to give you a brief survey of what simulations can be done, and this is something that we can go briefly from very simple to more advanced as we go along. So we can essentially do very simple model calculations using. So these are model calculations where you are doing stratification with four-fold anisotropy. And you're asking the question, okay, this organize evolving, what are the structure that it takes? This is the classical way HSP is utilized for. You essentially know what microstructure you are during certification. So the dendrite is one of the classic structures that you can model using FaceFill, and this is something that it can be done in the face in our software as well. So this is a single phase certification, but you can also do slightly complex stuff where you essentially have multiple phases. So what you have is a dendrite of a given orientation sitting over here, but you also have a dendrite of rotated orientation, essentially a different grain. So metallurgically, this would be a different grain that is certified. So you can have a constitution of different grains that are evolving from the liquid at one given time. So it gives you possibilities to do multi-grade certification, which is typically what you see in a casting, in a real world scenario. Okay? Similarly, you can also do precipitation reactions. So this is a precipitation reaction showing you the classical coarsening phenomena that happens during heat treatment. So what you see is that the larger precipitates are growing at the expense of the smaller precipitates, and that just happens because of coarsening. Okay, so this is something that can be again done in 2D and 3D. Not only that, you can also do the classical simulations. I don't know whether you have it visible on the screen over there. So on the right, that you see is the classical coarsening without the influence of elastic stresses. But here, what you have is the elastic stresses playing a role, giving you a certainly different microstructure, and that is just because of the influence of elastic stresses due to coherency. So these precipitates that emerge are coherent with the matrix, and thereby the stress that is associated with their nucleation and growth. And that stress will influence the shape as well as the coarsening dynamics that evolves. So it is important to capture that. As you see, the microstructure is remarkably different from the case where the elastic properties are not present. Okay. So a little more about what are solvers in terms of the capabilities of scaling are. So our solvers are capable to execute on thousands of CPUs. Okay, and this is one of the some of the runs that we executed on the Pravega machine at the Indian Institute of Science. So our Pravega machine has 28,000 CPUs in total. So we can essentially do very large runs, and these are the first runs that were performed on that system. So on the left is something that you see, the same simulation that I showed in a smaller setup, but here it's slightly larger, where you have essentially 4 million points in the domain. And we use 4,761 CPUs for about 3 million iterations in the problem. And what I want to show here is essentially the scaling of our solver. So if you were to make this domain 4 times larger, that is, you double the x coordinate and the y coordinate both by 2, so you get into 16 million points. And you essentially make the number of CPUs 4 times larger, so 19,044 CPUs. Essentially, you have double the problem, make the problem 4 times larger, and also increase the resources 4 times. So ideally, you should take the same time if your solvers are scaling properly, and that's precisely what it does. You take 3 hours for the same million number of iterations. So this essentially shows you that our solvers, the CPU solvers essentially, and the GPU solvers as well, scale very nicely. And that is very important, particularly to utilize the HPC machines as part of the NSM mission effectively and efficiently. Right? These are powerful machines, so it is important to utilize the hardware capabilities in a fruitful manner, and our solvers allow you to do that. Okay. Secondly, you also have GPU solvers. So this is parallelized using the OpenCL framework, where you essentially, so in the GPU, so the NSM machines, you have multiple CPUs, but you also have dedicated GPU nodes, where you have GPU graphic processor units sitting on some of the nodes. So we have essentially developed a strategy where you can essentially not only parallelize on the CPUs, but you can also use the GPUs. The GPUs essentially give you excellent compute capabilities because you can distribute your tasks on lot of cores. These cores are slower than an individual CPU core, but they are more in number. So essentially, if you can distribute the task into very fine kernels, such that you essentially give only a specified task to a particular GPU core, you can essentially, if you distribute it efficiently, you will get more work done, although each core is slower than a CPU core. Okay, that's because of the sheer number of cores available on classical GPU machines or GPU cards that are available even on your simplest laptop that is available to you. So this is something that is there, and these are some of the simulations that are done using the OpenCL framework. This was so Dattani Mohan, who was part of our framework. He is a PhD student. He was a PhD student with Professor Kumar. These are simulations for eternity, 3D simulations, and some of the simulations, if you look at it, they are over 1,000. This is a 1,024 cube simulation. So over a billion points that you are simulating, and for a realistic simulation that you need to do, you will typically hit these type of numbers. And therefore, if you want to extract these type of simulations out, you will need to access HPC machines, and our solvers allow you to do that. Alright. Similarly, this is a simulation for an additive process. In additive processes, typically what you have is that your microstructures will be very fine. So you essentially have, instead of dendrites, you will get cells, and you need to capture them with slightly smaller than the resolution. And therefore, these also can be captured using the sort of solvers. So what you see is, from classical physical problems, fundamental problems, you can also do applied problems using the same software, which is what we wanted to essentially address in using our software. We wanted to have software which allow you if you want to address something very fundamentally at a model development level, the tools are available for you to play around and change. But we also can do whatever is available, we can also do applied problems. So that is something that we have built into the software. Something else, this is something again a classical applied problem that you can do. So for example, this is an open source module that is existing for multiphysics. It's a multiphysics solver module. So some of you who haven't heard about OpenFOAM is again an open source software. It is classically utilized for CFD problems, computational fluid dynamics problems. But if you look at the structure of the problems, it's essentially a PDE solver. Okay, so and the PDE solvers are written in a way that you can code any abstract equation very simply because the operators are already present in the module. So since we are solving PDEs classically in a phase field formulation, we thought of utilizing this multiphysics OpenFOAM module and essentially put them into our stack. So what this is essentially a casting simulation where you are essentially cooling down a given amount of liquid at a given rate. Okay, and while you're doing that, you're asking the question: what is going to emerge as the solidification microstructure? What is the segregation that is going to be emerging? And why are these important? The segregation, as you will see over here, not here actually, but the segregation is evident in this curve over here. So I will just speed up these graphs a little bit. So these are the nuclei that emerge from the liquid, and as these nuclei emerge, these are multiple planes. As you see, each of them has a different orientation, right? This is the orientation field. So each color is an orientation, and as these grains are growing, because you are expecting temperature, heat, you essentially get into a structure which is what you would typically observe under a microscope. Okay, this is what you would observe, a multi-grain structure in a microscope, and this is something that we can simulate for a given cooling rate. So you can extract out of the simulation the temperature versus time curves, which is, you see, although you are expecting heat at a given rate, the temperature history is not linear. And that is because there is latent heat that evolves during solidification, giving you this monotonic decrease in temperature. And this is something that is important to capture, particularly for any post-processing that you want to do with this alloy. Similarly, you can also extract segregation, that is, what is the liquid composition, as an average liquid composition as a fraction of the solid that emerges. Why is this important? For any post-processing heat treatment that you want to do to this microstructure, which is typically what you do in any post-processing of a solidified material. So this is the same simulation for a much larger scale, and we use scalability of the multiphysics modules that are existing in our software. So second, you also have, apart from solidification, as I said, you also have precipitation simulations. So this is our graphics user interface. In the graphics user interface, on this end, what you are plotting is the evolution of the precipitation microstructure. So you are reinforcing But while you are doing coarsening, the interface allows you to process certain things about the microstructure. So
I don't know whether it's visible. You see this
dot that is evolving, and the dot is moving with time. So what we are plotting is the number of precipitates as a function of time. Okay, and so number of precipitates as a function of time is a measure of the coarsening process. So we can do other things as well. We can essentially.
So what is the blue one is liquid?
No, this is matrix. This is precipitation. So essentially, you have one solid emerging from the other solid, precipitation. And while it's doing, because it goes from a dwarf to a coarsening regime, you will see that after a certain stage, you have the larger precipitates growing at the expense of the smaller precipitates because the saturation in the matrix runs out. Okay, and you can plot several things.
It is happening after solidification.
This is a process that would typically happen during heat treatment that follows solidification. Okay, so you can basically have several things mapped out of the microstructure. So it's not only important to simulate a microstructure, you need to compute things out of the microstructure because that is what is the physics. That's where the physics is there, and this post-processing toolbox that we have, which is integrated to our simulation module, allows you to do that. Okay, so it is a the simulation module is closely connected to any post-processing that you will do in the mind. Okay, so very important to have that, and we have. So in terms of uniqueness of what is present in the market, both in terms of open source and commercial, this is something that is unique. Okay. So this is again a simulation of a multi-component nickel-based superalloy precipitation, and where you see these precipitates are no longer circular, but they have squarish shapes, and that is again a consequence of having coherency in the microstructure, giving you these things. And again, the question is, so from these simulations is, what is the volume fraction after a given time of heat treatment, which can be correlated to classical metallurgical properties like strength, creep strength, hardness, all of these. And once you are able to correlate these to the microstructural features, it gives you a strong handle how to control and design your heat treatment. Okay, so that's where these modeling capabilities will be utilized, and that's what this software allows you to do. So you can do single phase precipitation, but you can also do multi-phase precipitation. So, for example, this is when you are doing precipitation, typically because of the symmetry of the system, you can have different possibilities for the precipitate orientations depending on the crystal structure of the matrix from which the precipitate is evolving. So here is the possibility of the situation where you have two precipitates, one elongating laterally and the other elongating horizontally. Okay, and that is something that you can simulate in a multi-phase framework because the solver already has a multi-phase, multi-component capability already existing. So, okay. Similarly, you can do. So I'll show you one nice thing. This is something that emerges. So what you see over here is because of the different variants that come out of the matrix, you have a organization, a self-organization of the precipitate that emerges. Something very similar to the first movie that I showed you today, which was of the directional solidification, where you have organization happening just because of the interaction of the diffusion fields. But here it is more than the interaction of the diffusion fields, you have interaction of the elastic fields that emerge because of the different precipitates that are existing and their types. So they essentially self-organize to minimize the elastic interactions, thereby the energetic cost of growth, and that's something that is nicely coupled because of its multi-physics nature problem. Right? So such nice simulations and some essentially somebody from here was condensed matter physics, right? Who wanted to do condensed matter physics? Okay, anyway, so if you are essentially the classical condensed matter physics person, this pattern formation is the classical way you look at these problems, and this is something that can be addressed. Apart from the classical metallurgical context that you already have. Okay, so you can also do grain growth problems. So this is something that we have. So you can essentially have under certain conditions the grains growing and evolving, both in 2D and 3D. This is something that you can do. You can do multi-grain, as I said, the solidification using open foam in both 2D and 3D. The open form solvers utilize a slightly different way of doing multi-grain compared to the other solvers. We use what is known as the orientation field. That means the orientation of the grain is treated as a field which evolves with time. So you start from a distribution of the orientation in as a field, and that is a function which evolves with time, giving you multi-grain pseudo-identification. Now, if you think of orientation in 2D, it's a nice just one angle suffices to describe orientation. As soon as you go into 3D, you need 2 or 3 angles depending on how to describe the problem. And here is where we utilize the Quaternion framework to address this multi-grain problem. So this is essentially Tanmay's contribution to our software, where he has been able to do multi-grain certification using the Quaternion framework. This is already building upon literature already existing in phase field, but we just have integrated that particular modeling framework into MicroSim and have been able to treat multi-grain certification problems. Okay, so some features about post-processing. So apart from the classical sizes of the precipitate, surface area, volume, velocities that you can extract from any phase field simulation, you can also do some non-trivial stuff. For example, here you can extract the number of triple points that are. So these yellow points that you see over here, which I think are visible a little bit. So these yellow dots that you see are demarcating the triple points. And why are triple points necessary? They can be utilized for higher length scale models. So for example, you have the trajectories of these triple points as a function of time. You can essentially write graph-based solutions or even machine learned solutions of how the evolution will happen without actually needing to go into a phase field simulation framework. So we essentially learn from how the grain growth evolves, and thereby translate to a faster simulation, allows you for integrating and doing higher length scale simulations where you don't really want to do a phase field simulation. Okay? So this is something that, so on the left you have a box model, on the right you essentially have a phase field model of grain growth, both giving you essentially the same phenomena of grain growth, but using different strategies. But in both of them you can utilize and extract the trajectories of the triple points, right? And we also have a quadruple point calculator in higher dimensions. These points will not be visible, so that I'm just going to mention to you that it's there, that you can essentially compute both triple points, and these white dots that you would see over here are the coordinates of the quadruple points that you can extract from a simulation. This is something that is relevant for anybody who wanting to do the multi-scale type of models that I have shown in the first graph. Okay, and that means you essentially do a solidification problem, and after solidification you typically do a heat treatment of that material. Now the question to a process engineer is, okay, I have solidified this. How do I heat treat it? That's the question you typically have, and the question is, if you heat treat it, what properties do I expect after this heat treatment? That's essentially the question you want to address as a modeler, and thereby give some feedback to the actual process engineer who is doing something with the. So how does it? So in this framework, we have added something called sequential multiscaling. That means you do a solidification simulation, and since solidification simulations are essentially done at a scale which is much larger than the heat treatment scale, so typically if you want to do the same on the same domain of solidification, the heat treatment problem, it will become computationally very intensive. And that's not required also, because essentially they are operating at typically 2 different length scales. So what you do is essentially you do a solidification problem like it's there here. This is essentially a solidification of an atomized droplet. Okay, so how many of you know about inert gas atomization? So they essentially a procedure to make droplet powder from during for additive manufacturing or any other process like sintering and so on. So when you do inert gas atomization, what happens is you essentially squeeze liquid through a nozzle, and when it squeezes liquid through a nozzle, essentially velocity becomes high, and you break up into droplets, and these droplets solidify, giving you the powder. Okay. Now, since you have powder, one of the questions is that these powder will evolve during the solidification, giving you some microstructure, some segregation. But what you essentially want to do, let's say you want to pack that powder into something that is a uniform product, using sintering processes, the properties will depend on the microstructure of the product and the segregation that you do. Not only that, the processing that you need to give to that powder to achieve your product, those processing conditions are also dependent on the powder microstructure and the segregation. Therefore, for certain conditions, you would essentially want to know how is the powder solidified, what is the microstructure that emerges during solidification. Not only that, let's say you would like to do some post-processing with that microstructure. Let's say you want to give some packing, sintering to that using that powder. What microstructure evolves then? Okay, so this is something that we can do. So this is a droplet solidification that has been performed, and what you are now seeing is a procedure to extract from this microstructure a particular part of the domain that you are interested in and do a corresponding heat treatment calculation. Okay, so this is what will happen. So in the movie we see the extraction of a particular part of the domain. So there is a tool to extract the particular region of interest. Once you have taken the region of interest, you will essentially mesh it appropriately such that you can do a lower length scale simulation and then launch the heat treatment simulation using a different insight. So this is something that you will see. He had extracted that this region of interest is where he wants to know the precipitate distribution after heat treatment, and he will essentially launch something here. Okay. So let's pick this up. So once you have done this, you have the composition. You will regenerate thermodynamic properties using the thermodynamic databases that you have, generate the insight, and then you are ready for your heat treatment simulation. Okay. So this is what we can do as a heat treatment simulation of a small part of the microstructure that has evolved during solidification. A very powerful technique, particularly because different regions of the microstructure will evolve differently. So you can extract those different regions separately and ask the question, how does the precipitate distribution in those regions differ in terms of the distribution?
Basically, this is a coupling gap.
It's a coupling, it's a sequential multi-scaling type of thing, because then you can say, okay, this is depending on the microstructure variability in the different regions. This is what you expect in terms of the property variability. A very important input to any process parameter. Okay, so this is a latest addition to our software. We can now integrate flow using lattice Boltzmann to our modules. So on the left, you see the classical dendrites that you showed you were nice symmetric dendrites that were four-fold and so on. Flow can essentially spoil the symmetry of the problem, because flow is typically, if you look at gravity-induced flow, is induced in a particular direction, and you will essentially have the shape of the dendrite being altered because of this. And this is typically seen in experiments. It's important, therefore, to reproduce them. So this is, for example, solidification due, and principally it is being influenced by the buoyancy effect diffusion. So you essentially have flow upwards due to diffusion, and you see because of that, one region of the dendrite goes faster than the other regions, simply because of the flow convection, there is material transport that is associated with the convection, taking material which is required for the growth into certain directions and taking away from certain other directions, causing the asymmetry. Okay, and this is something which is very niche that comes out of phase-field simulations. They can give you very startling insights. For example, here, this is the classical directional solidification problem, where you have a planar interface which is moving at a given velocity, and you know that the planar interface, for most people in solidification material science, that will essentially destabilize beyond a critical velocity, giving you a cellular and a cellular to a dendritic transition. So this is what is happening over here. But as you are evolving into a cellular and a cellular to dendritic transition, because of these regions over here, where the composition segregation happens, you essentially, and because buoyancy is related to the segregation, you will essentially have a situation where there is a variability in the density of the material. And because of the variability of the density of the material, you will have flow. And this flow patterns is what emerges out of this calculation, which is certainly very beautiful to look at. And this has also been seen experimentally. So these vortices that people that form are present in experiments in literature. So it's something nice. It's important to know that this flow can essentially destabilize the structure that emerges, and therefore important to capture. So this capability has been will be out in our next release, which will happen in July next year. So we are putting together all these things. Okay. So in summary of all the features that are available, essentially all our solvers are three-dimensional. That means you can essentially do realistic problems. We have the capability to parallel using MPI, the classical message passing interface, CUDA, OpenCL, and as well as use OpenFOAM and Amrex types multiphysics solvers. You have Amrex solvers, which Venkatesh develops in his group. Amrex is another multiphysics solver capability where you essentially get a framework where the parallelization is fairly straightforward. So you have already libraries or a way to write code where you don't need to spend too much time into how the interaction between the processors happens. That is being built, and you can essentially develop on the framework already established. So Amrex solvers are present for multi-phase precipitation and solidification. In addition, Amrex solvers give you the added flexibility that you can use the same code for CPU and GPU. So, for example, the difference is the CPU code that we have here can run only on the CPU, but we have an alternate CUDA code that runs on the GPU. But we want to have interchangeability. That means you can have the same inside. You can launch using the different solvers on CPU and GPU separately. But the difference with the Amrex solvers is that you can launch the same code, and choosing the script how you launch the simulation, you can choose to launch on the CPU or the CPU. This is another partly on the OpenCL based solvers as well, but this is more accessible with the Amrex type of framework. As we said, we have a host of post-processing tools. Some demonstration of it will occur during the tutorial sessions as well as on the final day when we are essentially discussing them. For ease of installation, we now have singularity images for installing, where all that you need for your solvers is packaged as a singularity image. So you can just, irrespective of what exists on your machine, you can put that into your computers without affecting any other installation. You will be in the singularity branch, do your calculations in the singularity branch. When you have finished the calculation, you will exit from the singularity branch. You are done with it. Right? So you only install the environment that you need for installing any of the solvers, and then work with the solver and get it. So we have them for both Linux-based solvers and Windows-based solvers, which allows you a wide variability of flexibility, which was not there before. As I said, the new addition has been a 4 module, which is this is going to be something which is very nice that will be added and which will solve sort of try to address the type of problem that I showed in the multi-scale nature of typical materials problems, is that you have continuum, mesoscopic, and process simulations. Our attempt will be to integrate the process and the microstructure in a certain manner. So this is an example of what we will be trying to do. So here is the process solidification problem, where we are essentially having the solidification, the ink extraction from a droplet, but we are also doing microstructure. So you are coupling process and microstructure together in a particular problem, giving you this. So this will be something that will add different possibilities to do slightly different process conditions, impose them on the system, and extract what the microstructure evolution will be. Okay, so this will be a coupling where you are essentially doing process simulations in a diffuse interface framework, but getting the and coupling it to the microstructure. Okay, this is something that will be added in our next release for certain relevant materials problems of interest. So, for example, this is droplet solidification. On the right, you see a Bridgman solidification. So, what we are essentially having, how many of you know what a Bridgman is? You know a Bridgman. So, Bridgman is essentially a setup where you can do directional solidification. So, what you essentially do is you take a material, you have a furnace which is hot, and you typically have something below the hot zone of the furnace, which is a cold zone. You extract material. So what you typically do is essentially take the material in the hot zone, make it molten, and then you slowly extract the material into the cold zone. So you're essentially taking heat out in a particular direction and also controlling the velocity at which you pull out, so you're controlling the cooling rate. Okay, the reason you do this is to make classically directionally solidified materials. That means your crystals are going in one direction, and if you control it appreciably, you can actually get single crystal materials. And single crystal materials have a lot of applications, both in electronics industry as well as the aerospace industry. So different types of things. So some of the questions there are essentially, what are the conditions that you need, for example, to control the process such that you get the particular microstructure of interest, and therefore you need to again link the process that is the business with the microstructure that emerges, and therefore it becomes a something of interest. So we have a diffuse interface to framework loaded into OpenFOAM, which will be released as part of our next release in July, where we have a possibility to extract essentially the thermal history that is evolving during the cooling. So you are doing the thing, and how does the material cool, and particularly what is the shape of the solid liquid interface that emerges during the cooling of the material. Okay, and this is something very interesting because the shape of the solid liquid interface, for example, determines whether you get single crystals or DS alloys or nucleation and all of that. Okay. The interesting part is once you can do the process simulations in the same framework that you are going to do the microstructure simulation, we will essentially develop a framework where you can extract, like we did in the sequential multiscaling problem, you extract the particular relevant temperature area of interest and do a lower length scale microstructure simulation in the same framework because they are at different scales. So we essentially want to develop it. So this is something that we will develop. In addition to that, we will have the inhomogeneous elasticity. So if you look at the Fourier-based solvers that are present in our repository, you have the CUDA and the OpenCL frameworks. So they solve the elasticity using the Fourier. You will map the problem into Fourier space because it becomes efficient to solve. Okay. The only one is the inhomogeneous elasticity solver, where the elastic properties of the precipitate and the matrix are different. In that case, the problem becomes iterative, and you need the iterative solver to get to the mechanical equilibrium problem. So this is presently not there in our solvers. It will be added in the next phase. In addition, Abhik Group is working on futuristic branch, which is sort of going to become the programming standard as we go along. It's essentially the SYCL branch. So OpenCL will become essentially SYCL, and the idea is the same. You have the same portability of the code utilizing both CPU and GPU. So we're going to do modification in the code. The same code will run both on the CPU and the GPU. So that is something that will nucleate in our next release, and it will develop as along as we take things forward. One more example of coupling microstructure and process simulations is going to be. This was supposed to be a simulation. Somehow it is not there. Okay, doesn't really matter. This was an additive simulation where you have a deposition being modeled in a liquid interface framework, and the microstructure that comes out it appears over there. For some reason, this is slightly different. Doesn't really matter. So our NSM first frame, our first NSM project essentially ends in March this year, and we will have a launch of the next one depending on how the things are. But here are some directions in which you want to take our software. Because you are particularly users, we will essentially get funding from different places to keep the software going. In that sense, I would like to put out some directions in which we think of advancing what we want to have in our library. So if you look at NSM 1.0, our principal developments were essentially catering to the metallurgical industry, which means the classical solidification, precipitation, grain growth, recrystallization, all of that. What we want to do in NSM 2.0 is to develop tools for the device or the electronic industry, where we are essentially looking at multi-physics problems of more multi-physics. Here also there are multi-physics, but more multi-physics on the electronic and the magnetic properties and predictions. So here, for example, we would like to have the capabilities for ferroelectric ferromagnetic domain transitions. This is something we want to integrate. Then we want to integrate reactions for electrochemistry involved. So electrochemistry has wide-reaching implications for device fabrication, particularly if you are looking at porous materials. Also, if you are wanting looking at battery applications, where you are looking at wave transformations during charging, recharging, and how does that influence the performance of the battery. So a host of things that we can do with respect to once you put in electrochemical reactions and add them to your framework. So this will be something that we will add. Secondly, as I spoke before, failure mechanisms like electromigration and thermomigration is something that we have as capabilities but not integrated as part of MicroSim. So this is something we will be adding on into so electromigration, thermomigration, particularly relevant for predicting failure in during materials functioning in electronics industry is something that we will be adding. Fracture is something that we want to emerge towards. Fracture is a principal mode of failure. We want to add models where we can predict crack growth. So, for example, here is a crack growing. So, I don't know whether you can visualize this. This is essentially a crack is growing and splitting into several small cracks, and you're essentially following that crack while it's growing. And this is the microstructure that evolves. I'm calling it microstructure. It is essentially a structure of how the pattern of fracture happens. This is typically something that you would want to study fundamentally, as well as if you were to. So fracture is relevant at several scales. You can essentially have fracture relevant for classical materials problem, metallurgical problems, where you're essentially wanting to know how does the crack propagate, how does it add toughness in a given material. But you also have it in electronics industry. You don't want materials fracturing, and you want to find strategies to arrest crack and make it more tough. So fracture, predicting fracture and its formation is something which is of interest for all communities. It is also of interest fundamentally. Mathematically, fracture is still a problem where it can give rise. The study of instabilities during crack propagation is a mathematical problem. So it's something that can be addressed both by simulations and by analytical approaches. This is the last thing that we want to add in the next scale, which is essentially to do with plasticity. Plasticity, if you look at it, can be addressed at different scales. You can you're essentially asking the question: if you deform the material, how is the deformation going to happen? And it will in response to a given stress or a given stress rate. So essentially, if you were to treat it at the macroscopic scale, you are not really interested in the classical microscopic features anymore. But essentially, at the macroscopic level, what happens is you have dislocations and interaction of dislocations, giving you rise to complicated or complex mechanical behavior. So we want to address plasticity at different scales. There are different approaches. At the abacus and the ANSYS level, you have some way to write down constitutive laws for how damage happens. But you essentially must have the microstructure informed, and thereby some attempt has to be done to address derive those constitutive laws from microstructure phenomena. And here is where we will try to integrate with classical dislocation dynamics models and integrate or develop constitutive laws for macroscopic descriptions of plasticity. Right? So this is something that we also want to integrate. So with that, I would like to end. This is again the team of developers. I would like to emphasize that whatever you see today in the combination of not only the developers who are sitting here, some of the developers are already moved on into different positions elsewhere doing postdocs, but not only them, other developers, but it also is, as I said, the work of past PhDs on whose work the things have been developed. So the past PhDs and the unit, not only PhDs, master, UG students, the developments that have happened incrementally have been integrated in this framework, and that's how this has culminated into this particular software. So this will continue to happen as we go along, adding more and more capabilities. But that's essentially what to add. And then thank you for your attention, and we'll be happy to have some questions. Yeah, I think we have a team. Yeah, we are just in time. Yeah. So if any questions are there, you can just ask.
Guys, some of us.